All right, recording. So, the first thing we want to look at is just the output of any old distribution. Let's start with something really simple like a, am I in it? Yes, sweet. Something really simple like a piecewise function, which is a value of 1 between 1 and 2 and 0 otherwise. So that's, I'll draw it on the board. Can't be seen there, but it's not really relevant. First number, I might just bold it for clarity. Let's say equals, the first number can equal rand between, so that's going to be the function. Just want to make it normal size. Equal rand between, now we want 2 and 4, but we want 1 decimal place. Rand between only outputs integers. So what you have to do is for your bottom value, make it 2, but we're going to times by 10. So really the lowest one's going to be 20. And the biggest one's going to be 40, so we're going to get numbers between 20 and 40, but at the end we're going to divide by 10. So if we get a number like 25, dividing by 10 will give us 2.5. So it gives us the option to have those values. So 2 times 10 for the, well, we can just write 20 for the smallest value, 40 for the biggest, and at the end divide 10. So slash 10. Now I got the number 3.3. So I'll just click that function again so you can see the code at the top. Rand between, make sure you put equals at the start, equals rand between 20, 40 and divide by 10 at the end gives us a decimal between 2 and 4. And I got 3.3, you may have gotten anywhere between 2 and 4. At this point, if we start pressing F9, you may have to press function F9 on your device because you might have something else as F9. If you press that, oops, that's what my function F9 does, just F9 will refresh the workbook, which refreshes that value. So it'll keep changing between 2 and 4. Second. We're going to do 100 at first. So, anyone not up to that point or having trouble? Good. Once you've done that, can you copy that down 100 rows? So we're going to have 100 data values. So I'm going to scroll down. I start at 3. I'm going to go down to 103. Sorry, 102. Just as a reminder, to do that, you click your cell that you want to drag the code down for, and there's a little square there. I might zoom in. That little square in the bottom right corner of your cell, you click and drag that down 100 squares. If you're unsure, like say for example, I mean 100's all right, but if you were doing, this is only something I found out recently, but if you were doing 187 and you're starting at the number 59 and you don't want to do the math because sometimes it's inclusive, sometimes it's exclusive, how far down do I go? If you do it a certain amount, it will tell you down the bottom how many cells have you got highlighted. So my count is 100, so I got that right. So just double check that. It also tells you the average and the sum at the very bottom, which is interesting, without having to do a calculation. So we want 100 data values between 2 and 4. And I want to put them on a histogram. And this is the bit that's a bit time consuming, but it works nicely for my very, very mild OCD, is I want those histograms that we generate, we're going to generate a lot, I want them to always, including the sample mean ones, be between 2 and 4. If I just select this data, and well, more importantly when I get to the sample means, if I select the data and create a column graph and just remove the width to make a histogram, it's going to only make the boundaries of that histogram the minimum and maximum values. So if I have a huge sample, the average is the mean's going to be 3, by the way, by the end. But if I have a huge sample, say 1,000 sample means, it's almost going to only be 3 every single time. So my histogram's only going to be between like 2.8 and 3.2 or something. I want to show that as the sample size increases, the data trends towards a normal distribution in the middle, but I want to keep those endpoints. So, long story short, I want to create my own intervals here and then count how many times that occurs. So I'm going to create the intervals of 2 to 2.2, 2.2 to 2.4, 2.4 to 2.6, 2.6 to 2.8, 2.8 to 3, 3 to 3.2, and so on all the way up to 4. All right, those values are going to be our labels on our histogram. They're going to be the x-axis labels. So each bar is going to be associated with a range of values, and we're going to figure out the frequency of each of those ranges. So we should get, theoretically, a even distribution. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 100 values. So we should get a frequency of 10 in each of those rows. We should. We won't, but we should. Another reason we won't is because the random function in Excel, whether you use the random, R-A-N-D, or rand between, is not truly random. We can't make computers do truly random things because underlying the randomness is code, which is not random. So they do all sorts of things like making a seed based on the time of your device, and they do all sorts of things to make it as random as possible, but it is not. It simulates randomness. So that's unfortunate, but it's the best we can do. And I've noticed that Excel, typically when you do rand between, it gives you more emphasis, like it actually gives you more data points at the end of the distribution. So we're going to get more like 3.6s, 3.8s than 2.2s and 2.4s. It sucks, but it's close enough and it'll do our purposes. Just keep that in mind. So to count frequencies, we use the count equals countif function. And we want to say, we want the range. So the first thing is we want to select all our data points, or I'm just going to type A3 to A102. So colon in the middle to say I want between here and here. But here's the thing. And actually, I'll demonstrate the thing before we change that formula. And the criteria is I want to say how many are greater than or equal to 2, but also less than 2.2. So greater than or equal to 2, say 0.0, and this is where I might have to go back to my code. Yeah, I have to go back. I can't remember.
So you need an end function in there. So you can see end in like inside the count.
Here?
Yeah, there. And then you have that in there.
Thanks, mate. Less than 2.2. Close double bracket. The first bracket closes the AND function. The second bracket closes the countif function. If not, I did a different code, but it'll still work. Oops. What is the... Let me just go back and check. I'll copy and cut this. What did I use? I used this. Okay. We just need to put these thingies in. So in here, they just need to have speech marks, I think. Quotation marks? That can't be right. Sorry, I will come back to it. I just need to... that's what I used. Count ifs gives you multiple criteria to check. So we're going to change the start to count ifs, IFS, and then we don't need the AND function in there. The first one, make sure you only have one bracket now. The first, so count ifs, that range, comma, greater than or equal to 2.0, comma, less than 2.2, with apostrophe, like with quotation marks around them, I think it was. Do I need a square bracket? need square brackets.
You need to know the range though. Yeah, enter the range twice.
Oops.
Yeah, for each criteria.
Yeah, one sec. Do I?
Yeah, it says that.
Ah, yep, gotcha. Thank you. Alrighty, so in between here, we just can't change this to count ifs. A3 to A102, comma, greater than equal 2.0, comma, same range, comma, greater than 2.2, less than 2.2. Okay, good. That's the hard yards, by the way. So at the very top is my, so count ifs, select your range, comma, quotation marks greater than 2.0, greater than or equal to 2.0, comma, select the range again, comma, apostrophes. What do you call them? Are they called quotation marks?
Yeah.
Quotation marks less than 2.2. And it will count how many times they occur. Now, the only issue with dragging this formula down, as you will see, if I drag it down once, is that when you go down to the second one, it changes the range at which you're counting. So anytime you drag a formula down, it's also any cells you reference in that formula, it's going one cell down to look for that reference again. So we're going to have to force the original formula to have that range always, no matter what, even if we drag the equation down, which is where dollar signs come in. So I'm going to pause before I do the dollar signs. Anyone not up to this bit and needs a hand? Okay, all good. In front of the A at the start, put a dollar sign. In front of the 3, put a dollar sign. Also in front of the A102, dollar sign in front of the A, dollar sign in front of the 102. And the same thing for the second range. Dollar sign A, dollar sign 3, dollar sign A, dollar sign 102. I don't know why, but dollar signs make formulas in Excel look way more complicated. But really they're just saying, as you drag down, I still want to reference this range no matter where I drag this formula to. And you'll notice, as I drag down, it's exactly the same. What we need to manually change now is just the greater than or equal to and the less than bit. So in the second one down, I want the range of 2.2 to 2.4. So this 2.0 here, greater than 2.2 now, and less than 2.4. And you drag down again. Greater than now 2.4 and less than 2.6. Less than greater than 2.6, less than 2.8, and so on for all of them. So 2.8 to 3. If you double click like a number, it'll select the whole thing, by the way. So if I select the 2.8 and I want to change it to 3.8, I can just double click and change it to 3.8. And lastly, so go ahead and do that please, and then I'll give you a couple of minutes to do that. A binomial one, but if you wanted to look at say an exponential distribution, all you would have to change is the numbers that you're generating. So the code for those values, which we'll look at as well, changing to like an exponential distribution or a normal distribution you could do. And that way you've got it here and you don't have to create it again. Because one of the descriptors in the syllabus that you can't really be assessed on per se, but you need to learn, and it does deepen your understanding, is the cog verb in the syllabus is simulate. So it says simulate, blah, 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 and that's what we're doing here. Alrighty, so as you press F9 to refresh, you'll see a bunch of them change. Theoretically, we should get 10 of each, but as you'll notice, it pretty much never happens. Yeah, so if we now graph this, is anyone not here, by the way, and needs a hand catching up? Okay, you're all good. Okay, so highlight these. Remember, on the left-hand side is our labels, or our x-axis. On the right-hand side is our frequency. So if we go insert, recommended charts, but don't click histogram at the bottom because it sucks. We're going to use a column graph to make it a histogram. So just click the column graph. Yeah, okay. Make it a bit smaller probably. Now, chart title. Distribution. You can call it whatever you want, of 2 to 4. And to make this more of a histogram, I'm going to double click the actual bars. This may be slightly different on Mac if you've got a Mac, but you can figure it out. And then when you click these, the series outputs, you can make the gap width 0, which means that it turns into a histogram. So that's this bit on it. I don't know what it is on Mac. Probably same, yep. And then I also just want to make it easier to read, go to like the fill options and change the solid line and make the border black. That's just the border around each column. So we generate this guy. And now each time you press F9 and refresh, not only will the values refresh and the frequencies refresh, but your graph will refresh as well. And you can see it varies. But for the most part, it's representing that distribution that we've got on the board. It's a pretty even one. Nothing normal about it.
You go over that all the time, sir.
Pardon?
You go over that all the time.
Yep, which bit? Just the creating of the graph?
Yeah.
Yep. So have you got this bit? Yep. So select all your data, both columns, insert recommended charts column graph. I'm just going to resize it. From here, call it whatever you want. To make these bars touch, we need to double click one of the bars, which will double click all of them. And we want to go to this option, 3 lines, and change the gap width to 0. Yeah. Also go to your fill options, which is like a paint bucket on mine. I'm not sure what it is on Mac, and go the border to be a solid line. And just make it black. You can make whatever you want really, but. And so I'm just going to say distribution of 2 to 4. And great, so that's not anything to do with sample means, nor should it approach normality, because it's purely outputs from the values of 2 to 4, randomly. And it will change as we go. But for the most part, it's pretty uniform across the top, which is what you can expect from only 100 trials. If we did this with 1,000 trials, all those bars would be much more frequently even. But that's pretty good. Now though, the true bit, this is the central limit theorem coming into action. We want to, instead of sampling the raw results, I'm going to take a sample of 5 and then determine the mean of those 5. Okay, so I'm going to zoom out a little bit. Underneath my graph and column, and I urge you to do the same, just copy that original function we got, the ran between bit, and paste that into one of your cells. Oops. So you've got a new number. I'm just going to make all my things in the middle align. Drag that down that for 5 steps. So we should have a sample of 5. And underneath that sample of 5, I'm going to determine the mean of that sample. So equals average, select your range, done. And I'm going to bold it just to make sure I can identify that as the mean. Might even change it to this. So you should have copied one of these into a cell, or retype the function, up to you. Create 5 random numbers and determine their mean underneath. Now as we go, oh, it's 2 decimal places. I'm going to change it to just 1 decimal place by clicking that cell. Oh, can I force it to be 1 decimal place?
Yeah.
Yeah, I know, but like just force the output to be 1 decimal place.
A round function.
Yeah, on the mean.
On the average, so you go round.
Round, bracket, average, all that stuff. What do I put as my number of digits? 2?
I think it's 1 or 2.
Let's try 1 for 1 decimal place.
Yeah, 1.
Okay, cool. So before you do the average, guys, put equals round bracket. Do your average of those cells. And then after the average, put comma 1 for 1 decimal place. Close bracket. Now that's all well and good.
Rounds it, it still gives you that zero on the end. So you still got to do that regardless.
Mine's just got 1 decimal place now. Now, that mean that we've done, of course, any of these values here can be between 2 and 4. And that's what we found over here. The range of those values is going to be 2 to 4. Some are going to be 2, some are going to be 4, some are going to be in the middle. But what happens is that the mean of them, because some are going to be 2 and some are going to be 4, the mean of 5 is going to get closer to that middle part 3. And especially once we take hundreds of those means are going to get even closer and closer to 3 on average. So this is why the central limit theorem works and why it approaches the population mean, is because, yeah, you're going to have 2s and you're going to have 4s, 2s and 4s, but when you take a bunch of them and average them out, it's going to be about 3. And we can see that if we average the 100 data values we got, let's have a look. So if we, just next to it maybe, type equals average, and then A3 to A102, mine was. The average is 2.995. If I refresh, 2.933, 3.157, 2.93, 3.032, 2.9. And yes, there's possibilities that this mean is 2.1. It's possible that after 100 data values, the mean of them is 2.1. It's improbable, but it is possible. And so on average, because we can go from 2 to 4, it's going to average out to be about 3. Of course, there's a standard deviation that's going to change, but for the most part, it's going to be about 3. So what we want, it's no good to just, I mean, it is helpful to calculate a sample mean, but what I really want to do is determine a sample mean of 5 100 times. And then I want to take a sample mean of 20 100 times. I want to take a sample mean of 50 100 times, 100 100 times, 500 100 times, 10,000 100 times. And what we're going to find is the more and more values in each sample is going to make it more and more normal, the distribution of those means. So first things first, we're just going to do 5. So we've got our 5, we've got our mean. I want you to highlight all of them, and we're going to drag them up across 100. Now, across the top is unfortunately letters, but it goes up to Z, which is 26. Then it goes across to AZ, which is another 26. BZ, CZ, which is a bit over 100. So I'm going to stop it around CT or something and see how many are selected. So across I go. So C,
Oh my god.
T is way too many. What the heck? Oh, it's because I've got 6 in each one. I've selected 6, so I should have 600 as the countdown here. So I have to go across a few more. One more. There we go. It's to CX. So I started in, I think, row 15 in C15, I think, and I went all the way across to CX. But now I have 100 samples and the mean below each one. And you can see as we go across the bottom, the means are 3.1, 3.2, 2.8, 2.7, 2.4, 3.1, and so on, all the way across. Some of the means are bang on 3, but I'm sure if we go across, we'll see some of the means being quite high and quite low. Like there's a 2.5, which is way closer to 2, obviously, and it's just randomly, most of my sampled values were below 3, even though they were just as likely to be above 3. In that case, we'd probably have a really high 3 as well, somewhere along here. I'm not going to find it, but we could. And now, I want to, oh wait, actually, is anyone not up to there? Okay, I'm gonna grab my frequencies and my counts as before, because I don't want to have to type every bit of it again. And I might put it just up next to the distribution here, and up and to the right, I'm going to put my graph of those sample means. But this time, we're going to keep the same data ranges, but my count ifs is going to change slightly. So I always want to have the range of, in my case, I'm just graphing the means, the sample means. Oops. So it's going to be C20 all the way over to CX20. So I'm going to have $C to $20 all the way up to $CX and $20. If yours isn't the same, just check the start and end point of that row of means. Now in this case, we don't have to do that tedious thing where we go change all of these bits, the greater than equal to 2.0 and less than 2.2 and blah, blah, blah. All we're changing now is the ranges that exist in between. And every single one of these frequencies is going to have that exact range. So copy that, and to select it all, just double click. Control or Command C, depending on your device. And we're going to go through. There's 2 ranges in each cell. So we're going to change every single one of those ranges in that group of cells to that. So double click, copy it, and then to replace the other one, instead of like clicking and dragging and finding the right spot, just double click it to select it all and paste. For example, the next one, double click the range, paste. Double click, oops, don't triple click, double click, paste, enter, double click, paste, double click, paste. There's probably an easier way than this, but I don't know it. Does anyone know it? I want to check this one. Huh, no 2.4s to 2.6s. There we go, okay. They may be 0, it just means that the mean of all 100 didn't include that one. All right. As you go, you'll see the frequencies clumping up in the middle there. The familiar clumping of the normal distribution, perhaps. And when you're done, in the exact same way as before, create a histogram. So select all your cells, insert chart, that, bang. click.
That's just the simple units. Random function.
Oh, and when you graph, it's gonna be that. More or less.
And this is a sample mean distribution of n equals 5 because we've got 5 in each sample. And you can see straight away, even with just 5 in each sample and the mean of them, our histogram is approaching normality. Sometimes like this, it doesn't really look normal. It kind of looks negatively skewed. But other times, such as that, it looks like the histogram is giving you the finger, which means it is normal-ish. Now, I think what would be the most beneficial is seeing what happens as we make these, instead of n equals 5, maybe n equals 50. So, it's really the same process, it's that we just have to do it more of these. So, grab yourself a random value, or retype the function, whatever you want, paste it underneath. And this time, so I'm starting at, I know I can't see it on mine, but I'm at C22. I'm going to go down 50, so down to C71. I think mine will be. Yep, C71. Generate yourself 50 values. And underneath it, you can do the same command as before, equals round average C22 to C71, close bracket, comma 1 for the rounding decimal places, close bracket again, and I'm going to change that last one to be looking like that for mean calculation. 3 as expected, 3 as expected, 3 as expected, 3 as expected, 3.1, unexpected but possible, I suppose. 3 as expected, 3.1 as unexpected, 3.1, 2.9, but you'll notice 3.2, that was 0.2 away, 2.8 was 0.2 away, I'll keep going until I get 0.3 away. It's probably not going to happen. Anyway, 2.7. Once you've got 50, do what we did before. Drag, so 50 in each sample, do the mean, drag across 100 samples. The amount of samples we're doing is not changing. That's just to populate my histogram to make it look more populous, I suppose. But the amount in each sample is the important factor here. So drag it across to CX again. Pretty sure that means I've got 100. And it's in row 72. So the only difference I have to do now with my frequency table sort of thing is to change that range to C72 rather than C20 and CX72. So that will get me the means of the n equals 50 samples. And unfortunately, I have to do that for all of the frequencies. right, Kai?
Yeah, it's kind of, I don't know how, but I can't get it to work.
What bit are you up to? Oh, thank you. Sorry, Mel. So, back over here, can you please go to your very first random, and we're going to change that code to hopefully output a random value in our negative exponential function there. So, equals gamma dot inv for inverse. The regular gamma function, by the way, would take a value and output the probability, just like your cumulative PDF does on your calculator. Sorry, normal PDF does on your calculator, CDF. This one takes the probability and gives you a value. So our probability is going to be a rand decimal. So random, the function, R-A-N-D, bracket, bracket, outputs a random value between 0 and 1, which is great for us because we got asked to put in a probability, and any decimal between 0 and 1 is a probability. So that's our input. Alpha, as I said, was 1, no matter what. I don't know what that does in the gamma function. Beta is 1 over lambda. So if we're doing, say, a half, let's do 1 over a half, which would be 2. So if you weren't listening or don't care about that stuff, put in that gamma.inv, bracket rand, bracket, bracket, comma 1, comma 2. And hopefully it works. 1.201. But to keep it nice, let's do the round outside. Round, bracket, all of that stuff, comma 1, to make it 1 decimal place. And the value 0.9 is okay. But I'm just realizing we're going to need to change that, because they're only from 0 to, they're from 2 to 4, not from 0 to infinity and beyond. So that sucks. But what we're going to do is start at 0 and go to 4, and then at the very end we'll just say greater than 4, which will have a big distribution, but whatever, it is what it is. So please change, first of all, change all your values. So do that function in 1 and then drag it down 100 times. And just to double check what I should have as the boundaries, I'm actually just going to go equals max, what's my max value between A3 and A102? 12.4, holy smokes. That is unlikely. If I repeat it, 8.8, 9.5, 8.3, 13.3, 10.3, 8.6, 11.5, and so on, the minimum value is going to be 0. Okay, so it's going to go from, it's a negative exponential, so it should go from 0 to infinity. So technically we could generate a value that was like 1,000, but it's unlikely. 18. So we might go, that's going to change all of these, which is violently disappointing. How about, because we have 10 minutes, I'm going to do a ready, steady cook of here's one I prepared earlier. Here's the generated values. This is my sample size of 5, 100 times. Then I've done, I think, 100 and also 500 and maybe 1,000. And my graphs are on a different page, because why wouldn't they be? So, first things first. Danny, I want to just show you this. Here's what it looks like when you don't do the sample means. This is me just generating 5 values and plotting them, 50 values plotting them, 100 values plotting them, 500 values plotting them. Now, of course, I haven't got infinite space to make a histogram, so at the end, I'm always going to have this little uptick, which is just everything that was above 4.8, for example. If I went all the way up to like 10, it would be much more linear, but you can see when I sample 100 things, not means, just 100 data points, it's turning into that common exponential, negative exponential PDF that we explored in this unit. If I did 1,000, it would be even more distinct. So that's good. That's what the output is. So my gamma function's working. But if I look at the, if I take a sample mean and look at that, I think that's maybe somewhere else on this page. Maybe not. It does exist. No. No. Here we go. So, n equals 5. I took 5 of those exponential probability density function outputs, took the mean of them, did that 100 times. When n equals 5, it's kind of still exponential negatively. I'll keep refreshing. Excuse me. Still sort of exponential. I mean, it's, Kai, Luca, just watch this last bit. It's tending towards null, but it's still kind of that negative exponential. And it's just because the sample size is not big enough. In the other one, n equals 5 worked perfectly because we literally had a range of 2 to 4. Not very big. This range is 0 to infinity, but clumping up towards the end. As you can see, clumping up, but still got these outliers here. As soon as we go to n equals 50, so 50 random samples, and take the mean of each, it's much more normalized. We're not getting these means out here anymore. There's too many samples. So over here, this 4.8 could have just been 5 random values that happened to be clumped around 4.8. The thing is though, once you start generating 50 values, yeah, you'll get a series of like 10 that might be around 4.8, but then you'll get a series of 5 that are around 0.5. And then you get a couple around 7, you'll get a bunch around 2, and it'll even out by the time you've done 50 trials. That average, that mean, will be much more likely to be 2. Okay? Keeping in mind, when we did our initial probability density functions with exponential, we learned, and this may be a revision for you, that the mean of that sort of probability density function is 1 over lambda. So if our lambda is 0.5, 1 over 0.5 should be 2. So we should get, after a lot of trials, this thing should approach a mean of 2. And we can see that. They're already starting to clump around 2.2. As we get to E equals 100, even more clumped, E equals 500, perfectly symmetrical almost, around 2. This column is just less than 2, this column is just greater than 2. But no matter how many times I refresh, I've got 4 columns at most. Maybe I can get a 5th. There's 3 there. But typically 4 columns. 2 dominant columns with 2 little ones. Over here, it's a mess. I mean, you can see it's sort of approaching normality, but we still have this sort of exponential residue, I suppose, coming from the fact it was an exponential function. That's already gone by n equals 50. It just doesn't exist. So the whole point of today's lesson, the simulation that we've been doing, is to just understand more or less through simulation that no matter the input function, truly, doesn't matter what it is, if you take samples and find the mean of the samples and take heaps of samples, say 100, then the central limit theorem says if your number in each sample is greater than 30, then it should be normal. The sample means when you graph them, no matter the input. We looked at a binomial first. It was either 0 or 1. We also looked at a negative exponential probability density function, and it still turned out to be normal. If you did it with an actual normal distribution input, it would output as a normal distribution. Pick any function, and it will output the sample means to be normal. Sine of x, where x is a random value, it's going to be curvy, of course, the function that inputs, but if you average the means, it's going to be normal. It's just as much as below and above, but that mean will be 0. So that concept is underlying all of the maths that we're going to do with standard deviations and means and stuff. It is not explicitly going to help you in an exam. Obviously, you don't have an Excel in an exam. You can't be asked to simulate because our calculators can't simulate, but hopefully that helps your understanding of when we start getting to things like confidence intervals. I've heard a few people express they don't really know what confidence intervals are. When we get to them, it's really saying, if I pick a sample mean, for example, let's say here, I'm pretty damn confident that with 500 data points in my sample, I am very confident that the actual population mean lies between 1.8 and 2.2. I'm very confident. Say, for example, 95% confident. Whereas if I don't have many samples, I am not at all confident that my mean lies there, my population mean. Looking at this, if I just had to guess, I would guess probably between 1.5 and 1.4 and 1.8 or something like that. That would be my guess. But if I wanted to be, let's say, 95% sure I'm covering the mean, my range that I would be sure about would be 0.6 to say 4. I'm 95% sure the population mean, which we know to be 2, by the way, we know it. I'm 95% sure looking at this, it's 0.6 to 4. But as my sample size increases, the 95% confidence that I'm making the prediction on, it gets smaller and smaller and even smaller. So when we get to confidence intervals, that's why this is also important, because it shows you sample means and the confidence intervals relating to them is just looking at these histograms. How clumped up is the middle? If you have heaps of data points, very clumped up, so I can be very sure it's in a small range. I can be 100% sure it is 0 to infinity, or negative infinity to positive infinity, but we can never be 100% sure what the population mean is from a sample mean. But we can make predictions using the central limit theorem, I suppose. All right, 1 to 2 minutes before the bell. Any questions? I don't need to do anything tonight, but tomorrow we're going to be starting our confidence intervals, starting with also z-scores. Do you guys know much about z-scores? Yeah. Won't have to do much then. Going straight to confidence intervals then.